Welcome to the Cosmic Pie Podcast, Episode 22, Season 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting from the campus of the University of North Dakota here in Grand Forks, North Dakota.
Yep.
We do have a chat feature that's running, so if you have any comments or questions for us during the podcast, please feel free to send us what you have.
Yep. Try to keep it a little relevant to what's going on, but...
You don't ask anything about like baseball scores or who to bet on?
Yeah, I'm not going to have much to go on there anyway. Yeah.
Too early yet for football. We'll have to wait a few weeks for that to start up.
Yeah, and then that's all I'll be hearing from my friends. I've never been much of a sports fan, folks, so...
So taking your advice is like random, right?
Pretty much. I mean, I do like baseball, but I like going to the park and watching it.
I see, right.
And I'll agree with anybody, watching it on television is kind of boring, but when you're at the ball field and you see how fast that center fielder is running across the field and how fast a 90-mile-an-hour fastball looks, it's a little more exciting.
And there's a lot of physics involved in baseball.
Absolutely.
A ton.
Yeah.
In fact, if I remember, people have written books about the physics of baseball. Yeah.
A lot of intro physics problems and particularly upper-level physics problems are involved about predicting a baseball's flight path off of a bat and things like that.
Yeah, so projectile motion is the obvious thing. Impulse.
Air resistance, impulse.
Force against the base. Yeah, all that sort of. The spin of the ball.
All the Magnus forces.
And that's related to, airplanes flying, the wings and stuff, the difference in the air pressure above and below the wings. You think of a spinning baseball. That's what makes the ball curve. When you give it a spin. Yeah. A slider. Sounds like a small hamburger.
I'll add that since we've gotten onto that. I used to play one of the baseball games for the PlayStation or PlayStation 2. And this was back in the days when John Schmaltz was pitching for the Braves. And he had like 4 inches of movement on his curveball. And so one of the commentators on the game, when you were pitching as John Smoltz and would throw a curveball like that, curveball is often referred to as your Uncle Charlie. And they were like, that isn't your Uncle Charlie. That's the Lord Charles. And that stuck with me, the way they said it and everything.
But you just wonder how some of them hit that ball when it's doing that movement, right?
I played Little League, and I can honestly say I never hit one, so I have no idea how they did it.
That's why they get the big bucks.
That's why they get the big bucks.
Now, disclaimer for today?
Disclaimer for the day. The things being said are the opinions of myself and Wayne. They are not the opinions of the Department of Physics and Astrophysics, the University of North Dakota, or the College of Arts and Sciences, or anybody else. So you got to come at us.
And we also upload our podcast the next day to Spotify. So if you rather listen to Spotify, the disadvantage is you don't get to ask us stuff on the chat.
At the same time, thank you for watching. You know?
Exactly. So
please.
We like to have comments and questions if you have anything.
Right. And if you are watching on the recorded version, by all means, leave us a comment. So. Yeah,
exactly. So, first news item of the day, Robert?
First news item of the day.
We're being invaded.
We've got a space invader. Sorry.
This is actually the third one.
I remember the other one, the second one, Oumuamua?
Yeah, Oumuamua.
Something like that.
Yeah, that's Hawaiian for, I don't remember.
I don't remember either.
But that's where the name comes from.
Yeah.
And we'll talk about that actually a little bit later.
Okay.
In the sort of story here. So the news item is that it was discovered recently on July the 1st, which is actually the last time we did our podcast.
Right.
So unbeknownst to us.
This important thing was
happening. While we were doing our podcast, the Atlas survey, which was looking at the sky down in Chile, picked up this object that you see there on the left. So you see that sort of cross, and in the center of that cross you see the object, which has been designated as a comet. So it's not an asteroid, it's a comet. Now you might ask, what's the difference? Comets, you think of the traditional one, the nice long tail.
Right.
It streams out from the comet and the fuzzy head of the comet, the coma of the comet.
I was about to say, or as we sometimes like to say, the intermittent atmosphere.
There you go. So you can think of that, where an asteroid, you just think of a like large lump of rock that you're just praying it doesn't hit the Earth, this kind of thing. In fact, there is a sort of a continuous and range of properties in a lot of these objects. So some objects that look like asteroids turn out to be similar to comets, especially when they come closer to the sun.
And in fact, Ceres, if I'm not mistaken, surprised people when we sent a mission there. We found a lot more ice involved in that body, which is a main belt asteroid, but it has some very comet-like features apparently to it.
And we know these objects, for example, have what we call volatiles, and those are chemicals, combination of molecules that can easily evaporate from the surface.
Right.
So you have what's called outgassing. So you can think of, what was the movie with Bruce Willis?
Armageddon.
Armageddon. So you go to an asteroid, which is really a comet in that movie, if you remember that. And as soon as the sunlight would hit the surface, you have all these jets of material that was flying upwards. So the idea was to drill a hole while you're still in the darkness, before the sunlight, you start evaporating the cometary material to try to plant the nuclear bomb that would blow up the comet.
And there was so much wrong with that movie. Great movie, but there was so much wrong with it.
But the outgassing is a real thing. I mean, we've landed space probes on comets. The Fly, for example, from the European Space Agency.
Right.
And you can clearly see the outgassing that was occurring near the vicinity of the spacecraft. And of course, we've taken lots of images of comets from close up. I think Halley was the first. Comet Halley would be the first one in 1986.
I think so.
And that was the Soviet Union at the time had a mission to fly by, and also the European Space Agency.
And then we've since done some sample
this
returns.
was this was a time when there was a lot of cutbacks.
Right.
In the late 70s, and the United States, in particular NASA, decided not to send a spacecraft to rendezvous with Comet Halley.
Right.
So, and then when Comet Halley came its close approach to the sun in 86, people were like, well, what about the United States? What happened to us? I was like, well, sorry, because these things take a lot of planning, and you had your opportunity.
And you
decided,
for cutbacks.
Yeah, you decided not to do it. Just once in every, 76-year event?
Years, yeah.
So, unfortunately, the United States didn't do it. In fact, they actually, just to follow up that a little bit, they actually built a instrument telescope package that was launched on the Space Shuttle Challenger to go watch Halley's Comet. At least they were doing some science, of course.
Right.
And that telescope package, do you know what shuttle that ended up going on?
I don't remember, no.
Challenger.
Oh.
Yeah.
Oh.
In 86, January. The one
Yikes.
the time that it blew up.
Right.
So, of course, all the payload was destroyed as well as the astronauts, obviously.
Well as the astronauts, yeah.
So that's what happened there. That was NASA's try to take images of Halley. But we made up for it. We've gone close to asteroids and other objects.
Yep.
And comets.
Like I said, like I mentioned a little bit ago, we've done sample returns on them now. First time I'd ever heard of aerogel, as a matter of fact.
Right. So, the technology has improved.
Right.
And so we can do a lot more science nowadays than you could back in, the mid-1980s. Anyway, so this asteroid-looking thing actually turns out to be a comet. In fact, it doesn't have a long tail that you would expect a comet to have because it is just too far away from the sun now. Those volatile elements haven't been heated up, and no appreciable outgassing that's occurring on the surface.
Does have a coma already, though, right? I think.
Not that I'm aware of.
Okay, I thought that was one of the reasons they realized it was a comet is they started to develop the haze.
I'm not sure. I didn't see any evidence of that. Any images that would. I mean, you can look at the images.
It's a point of light.
Yeah, it's not much of a size to it in terms of number of pixels that it occupies.
Yeah.
People have looked for molecules associated with Comet. There was a paper that actually came out, I believe it was yesterday, last night's will be in today's papers, Astro Preprint Server, and they looked with a spectroscope looking for the different chemicals that you would associate with comets. Haven't found any yet. So if there is any outgassing, it's at a very, very low level right now. Now, stand by because, this thing is traveling extremely fast.
Yes.
And that makes it interesting because when astronomers detected trace back the orbit, what they discovered was that it's actually had come from outside of the solar system.
Right.
So that's the really exciting thing, right? Oh, if you said, I discovered an asteroid or it turned out to be a comet, nowadays people are like, whoop-de-doo, because there's literally thousands and thousands of these objects in orbit around our sun. The only time it seems to gain attention is going to come really close to the Earth and therefore really bright, potentially. Right. Or, and we don't want this to ever happen, it's on a collision course with the Earth. That would get our attention and make the news. Or, lately, whether or not it's on an orbit that brings it from some other star system.
Right.
And that's the case with this object, which is really interesting. Now,
well,
sorry, you're going to say something.
I was just going to say, it was some of those parameters that were of that orbit that were like, whoa, this is coming from somewhere else.
Now, you might wonder, how can I see this object? Well, it's in the constellation Sagittarius. So, Robert, where would you look for that, at least for the northern hemisphere?
Sagittarius, that'd be low on the horizon to the south.
Yeah, that's towards the center of our galaxy.
Towards the center of the galaxy, yeah.
So you can see the image on the right. That's like a larger field of view image. So you see more of the nebulosity towards the center of our galaxy, interstellar matter, and you can see that little zoomed in postage stamp showing you where the object is located now.
And then you move that postage stamp over to the left side, right?
Yes, exactly.
Okay. Yep. So.
Now, speaking about the orbit, here's the track of the orbit and gives you some information about it. Number one, it will make its closest approach to the sun in October. And notice the track that you see there, sort of like a curved whitish grayish line starting in the upper left and going out to the lower right. It'll pass by the orbit of Jupiter and it'll make it to inside the orbit of Mars, but not closer to the sun than Earth's orbit. And then back out again.
And
Go
ahead. No,
I was going to say, and so the closest approach then from the sun will be a little bit less than 1.4 AU. So you want to explain what an AU is for those who may not know?
Sure. An AU is simply the mean, the average distance from Earth to the sun. So,
which is about what, 93
million kilometers?
Miles. 93 million, about 148 million kilometers of that order. So it's going to come within 1.4 AU then of the sun. So close, but not that close. In fact, we don't have to worry about this object colliding with the Earth.
Because it's going to be about 2 AU at closest approach to Earth.
Yeah, and so the other thing you worry is this is just some random object coming in from some location, from another star system.
Right.
And we don't know because you could trace it back, but a lot of times in the past, 2 other objects, which we'll get into a little later, that come from outside our solar system, you don't know exactly where they come from. You get a rough idea, but you don't know exactly.
But even looking at this picture, you can tell it is definitely from outside the solar system.
Yeah, you can see the bend of the orbit.
The bend of the orbit, how little bend there is. That's the eccentricity, which for this object is 6. Now, an eccentricity of 1 is a parabola. 1 is a circle.
Yeah, 0 is a circle.
0 is a circle, right?
Right. 1, you could think of it as a straight line.
Okay.
Right, if you look at the limits of a circle.
See, I got to admit, it's been a long time.
That's a closed orbit. That's a closed orbit. Right.
Anything less than 1 is a closed orbit.
Right. So it's greater than 1. If 1 or greater, then it's an unbounded system.
And the larger that number is, the closer it's getting to a straight line. So this thing is coming in really fast at an eccentricity of 6. There's not much bend to that orbit. And it also looks like it's polar.
Well, it's extreme hyperbolic.
Extremely hyperbolic. And like I said, it looks like it's polar, like it's going under the plane of the solar system.
Yeah, it's definitely higher coming in above the plane of the solar system and higher going out, and the minimum at the closest point.
Right. So all of these things are any one of these things would be like, oh, well, it could come from the Oort cloud. But all of them together, no, this sucker came screaming in from outside the solar system.
And the thing is, you have to realize that it's coming in at a random direction.
Right.
Now, the chance, if you just drew a number, right, an orbital number, let's say, the chance of it making a direct collision course with the Earth is very, very, very tiny.
Right.
I mean, there's a lot of space out there, right? Even in our solar system, there's a huge volume that it occupies. So the chance that this would make a direct collision course with the Earth is really small. But it's a non-zero chance until you track and see where it's going. This case is a 0 chance it's going to hit the Earth. But if you just fire some random shot, you know, so it could easily have been, it could have been, I mean, the chance is low that we said, it's coming in extremely fast.
Right.
And it's heading directly towards us. Then what do we do?
Well, in the case of something coming in this fast, there's nothing that can be done. I mean, by the time you get a rocket prepared, it's here. It's October, closest approach.
Now this
2 months away. We can't build a rocket to do it that fast.
No, and this object is screaming in. I mean, it's only going to be in the inner part of the solar system for a month or two, and that's it. So even to catch up with it, even if we had a rocket that's ready to launch tonight, the chance of us that, you know how difficult the difficulty involved in catching this object, how difficult that would be? Okay, we have to do a lot more advancement in rocket propulsion to be able to take off in a jiffy, if you like, and catch something like that.
I mean, the European ESA, the European Space Agency, has even talked about for when one of these objects comes into the solar system to have an orbiter already in orbit around Earth, so you just got to give it a push to get it out there to intercept. Except with something coming in this fast, you know, eccentricity 6, it's coming in fast. You even with something already in orbit, you're not going to intercept it.
Yeah, for sure. So you can see this is where the object is located now. So this is the numbers as of yesterday evening. I took the calculations of the. So it's a distance right now of about 3.3 AU from the Earth.
Okay.
So it's going to close that distance to get to 1.8 from now till October.
In 2 months?
Yeah. So that's moving.
That's fast.
It is. And and you might wonder, well, then can I see this thing? You know, can I go with my binoculars or a small telescope, whatever? The brightness of it, and it's listed there as a magnitude 17.6.
It's going to take a little more than binoculars.
No, you need a large telescope.
Yeah.
Fortunately, I was going to say unfortunately, but we want to keep this thing far away from us.
Right.
So fortunately, it'll take a large telescope to see it because it's so far away. So it's extremely faint. In fact, it was hard to detect. You look at the Atlas survey, and the only reason why they detect it is because the thing moves relative to the other objects that were mostly stars that you're going to see.
Yeah.
And so it's the movement that gives it away. Right, it catches your attention.
Which is probably why it was spotted even at that low magnitude, is because it is moving so fast. It pings, it gets spotted.
It's like anything else in nature, right? You walk in the woods, and how do you see some animal that's normally camouflaged through its motion?
Right.
If you can see it moving, and that catches the eye rather than if it was standing there stationary staring at you, very difficult to see. Now, same as this.
I got to admit, I'm looking at this and I'm going, I never noticed that about the naming convention, but there's another Atlas object in this field of view, and it's a comet, C 2024 J3 Atlas.
Right.
It was found by the Atlas survey. It's a comet, C.
Yes.
And what caught my eye about that and made me want to mention it is that the object we're discussing is 3I Atlas.
Right.
And it's been also named C2025N1, 3I. It's the third interstellar object.
Bingo. Exactly right. It's the third confirmed interstellar object.
That's neat.
Yeah.
I didn't know they were naming, keeping track of it like that.
Yeah. So it's definitely a comet. It's on the list. As you mentioned, C's 2025 N1, so it's designated as a comet. But it's also an object that came from outside of our solar system.
So it's a 3I.
Where did it come from? Well, that's a great mystery.
Well, once you're out in interstellar space, you're being tugged by the galaxy, by the other stars. So
Klingons taking shots at you.
Taking shots at it.
You never know what you encounter, right?
You're right.
Now, we spoke that as the third confirmed interstellar object. Well, what are the other two? So here are the other two. So first of all, looking at the far left, that's Oumuamua. So that was discovered several years ago. This is an artist's drawing. It's not, we don't have it, the direct picture of it is just a pinpoint of light.
Well, I remember Oumuamua because it came in so fast.
Yeah.
It was here and gone almost before people realized it was in the solar system.
Yeah, if I remember right, I thought it would captured people's attention when it was on its way out.
Right.
It was already outbound. It had already
'Cause
swung
it
by
came
the
in
sun.
from behind the sun, didn't it?
Yeah,
Something like
I'm
that.
trying to remember, I thought that it was
Yeah.
already on its way out. So that made it even more difficult to get good measurements of because it's receding at a high rate of speed.
Right.
Now, they did take observations that showed that it was highly elongated, if you assume that the observations are correct. And some people
Always question.
that because we don't have really good high-resolution images of the object.
Right.
And so that's why you get this artist drawings. And I think the ratio was like 10-1. So it
Something
was
like
that's
that,
really
yeah.
bizarre. In fact, you know the whole story of
Oh, yeah.
Oumuamua and what happened with it in terms of its origin or nature.
Yeah, people started talking about it was an alien spacecraft or something.
Yeah,
Or an alien probe.
Yeah, there are people out there even today that think that it was an artifact of
Right.
some advanced civilization that's sending it's von Neumann-like probes, sending them all over the galaxy or universe.
The only thing is if it was such a thing, it didn't slow down. It didn't change speed.
Well, it did.
Well,
Okay.
okay.
There was some slight change in its motion, but that can easily be chalked up to outgassing that occurred.
Right.
Because if you look at the image, the artist's drawing there, you notice you see little jets on its surface. Well, each of those jets act like a little rocket.
Right.
So with a rocket, of course, you think of Newton's third law.
Third law of
Motion.
impulse.
Yeah, you're going to have a force, and that's going to cause an acceleration.
Yep.
And which means that the positioning or motion of the object will change. So its orbit can be altered over time.
Our initial description of this type of an effect is to get people to imagine they're on a sled on a lake of ice with a pile of bricks on the sled. And you can get yourself moving by picking up the brick and throwing it in the direction opposite to the way you want to slide.
Right.
So you don't have to push against something to produce a force. You just have to eject mass at a high rate of speed.
And that's how a rocket works in a vacuum of space.
That's it.
Now, the other thing is the heating of the surface of this object, depending on how it rotates, can even cause thruster reaction.
Yep.
So that's a well-known effect even for our own asteroids, that they alter their orbits or can slightly because of that effect.
Because of getting hotter on one side over
Yeah,
versus
and
the other.
that's right. And when they cool off, they emit thermal photons.
Right.
So that is a net momentum being released in a certain direction. That's a thrusting sort of action again, and that can change the orbit of these objects if you allow enough time to to
Enough
elapse.
time to come.
Yeah. But in this case, it would be the outgassing, which would be the primary thrusting action.
That's right, because it did go close to the sun, didn't it?
Yeah, and then if you allow enough to this occur, then you can possibly
Build up a significant amount of velocity.
you can explain the change in its orbit.
Right.
But of course, others out there said the change in orbit was due to the fact it's an alien spacecraft, and
my response
blah,
to
blah.
that is why didn't it swing back around for another look or something?
well, we
like
just
that,
don't have any
you know?
evidence that that's the case.
Right.
So you could make up anything, right?
Yeah, true.
It
was Bigfoot.
So, but boil it down to, always start with the simplest explanation. It's probably the thrusting of the naturally occurring outgassing that caused its orbit to shift.
Sure.
Not the fact that you immediately jump to the fact that it's a starship from planet Zulo and
Yeah, it was Bigfoot. Prove me wrong.
from what is Zeta Reticuli? Is that the favorite
I don't
place
know.
where the stuff comes from? And
I stopped reading at that point, which is why I didn't
and it's
remember
all
it even
and it's all,
happening.
it was actually launched from the Earth by reptilians that live under the ground
Yeah.
somewhere or whatever. Anyways,
Anyway,
so there's that object. Now there was plans to try to reach it,
oh, okay.
and I've seen
right.
studies that were done.
Yeah,
But the studies were like, we need to build this now, need to launch it within 5 years, because it's still there. It's not like it disappeared. It's in the outer solar system, still part of our solar system. It's just that it's very hard to get to.
yeah, and it's definitely on a open orbit, so it's going to leave the solar system.
Yeah, unbound once again. And, of course, we could get to it within 10 years easily.
Right.
But you know what it requires?
Money.
Moolah. So if we get some moolah from Elon Musk or something, right?
Yeah.
Or someone else
We
who
can
has a
chase
lot
it
of
down and
money,
find out.
has a little bit more money than you have, Robert, then
just
we
touch.
could then we could build a spacecraft, put it on a very powerful rocket.
Right.
In fact, imagine being launched by the SLS rocket that's going to send humans back to the moon, hopefully by next year or whenever, that rocket, and the mass of the payload is relatively small, you could probably obtain a really high rate of speed heading out of the solar system and maybe catch it. You have to do the math.
Right.
Right, to see if you can catch it within 10 years or something like that. So if we want to spend the resources, is what I'm getting at, you can catch it.
You can catch it.
And then you could take update nearby measurements, photographs. You can do spectral analysis. If you're going to go through all that trouble, why not take a mini lander with you, land on its surface, drill down into the material and sample it, right? Take an image of the docking module that's on. The boulders that will be on its surface.
Yep.
Wash the windshield. That's part of the space. You have a lot of fun with this one,
Yeah, absolutely.
And it's just a matter of money. Is it worthwhile to spend the money?
And I'm going to come down on the side of saying no, not really.
Well, we have the technology. It's not a matter of that. But it's not worth the lot of money. That it would be billion with the SLS launch. It would be over $1 billion.
Oh yeah.
So probably $2 billion. You'd have to, and you have to do it right away.
Right.
So you'd have to have people working on it, as rapidly as possible.
All that overtime that you're paying for.
Well, everything would be included. And then, do you want to send one, or should we send two? You go down that little rabbit hole for backup in case of failure of equipment or something, right? Computer dies, one day before interception or something, right?
Right.
Would not be good.
As Armageddon taught us, you send 2 drill teams.
Yes, exactly. Now, the middle picture, that's a real image. It's not a drawing made. That's a Borisov. So that is the second object that was recognized to have an orbit that's unbounded, that is not bounded to our solar system, that it was just a one-time visitor only type of situation. Yeah. And that definitely was a comet. And you can see the tail, part of the coma and everything. There's just a classic type of comet. And now, of course, on the far right is the new visitor.
Yeah. Now, I would like to point out, you can't have unbound or open orbits for solar system objects as well. They're just not going to have the rate of speed. They're not going to have the high eccentricity and other factors that we've kind of hinted at. But, there's that sort of thing that allows us to start telling and saying, okay, this is interstellar, or this is inside.
Yeah, well, you could have some objects that are way out in the Oort cloud that's loosely bound to our sun.
Right. That
any type of half-decent gravitational perturbations can upset their orbit and make it not bound, but now unbound.
Right.
So that could happen.
And we've seen a few of those.
And you can have objects that stream in from the Oort cloud on these essential. We had that recently, if you remember, the comet that came near the sun.
Yeah.
But it had an eccentricity of like 0.99999999998 or something like that, right?
Yeah.
So,
and with plus or minus 0.1. And so it was essentially, it was unbound because we wouldn't see it again.
Yeah. And those type of objects, like I said, could initially be bound orbits, but then it just takes a little bit of tug to make them unbound.
Pass too close to Jupiter and suddenly it gets eccentricity, kicks over one.
Yeah,
and
a
it's unbound.
very unstable orbit. It'd be like, for example, taking a pencil and trying to balance it on the lead point, not on the eraser end.
Right.
If you even could get it to balance, if you could, which would be, hat off for you to doing that, right? Then it's highly unstable. Any little wisp of air or puff of anything would flip it over one way or the other, right? It would tip over.
And so that's what we're talking about. Anything from the solar system is going to be at that real marginally close point.
Yeah.
Whereas these are not.
Now, of course, the first thing I think of when you think, we captured an object coming in, was it the Vera Rubin telescope? Because Vera Rubin should be able to pick up a lot of these type of objects.
Right. So maybe we'll start seeing the
a
count
lot
on them
more
going up.
Yeah.
I hadn't thought about that.
So how many of these objects did we miss? If they're so elusive, so hard to see, how many of them came through? And it doesn't have to be the inner part of the solar system, right? They could have only made it to the inside the orbit of Jupiter barely, and went back out again. How many of them did we miss?
Right, because again, that whole polar orbit business, how many of them came in, stayed out at a distance of about Jupiter because they swept on a polar orbit around.
Yeah. So the Vera Rubin should be able to pick up a lot more of these objects. So
Nice.
we'll have a better idea of the statistics, like how many on average do we get a year,
Right.
let's say, that pass through the solar system, the inner part. And then we could, have that to direct the type of potentially direct measurements by sending out, having spacecraft, maybe an ion thrusters, or in the future nuclear propulsion. That these things can zip around the solar system and rendezvous with these targets.
I'm still going to go on the side that says that these still should be relatively rare, because as we mentioned, space is big. There would have to be, quadrillions of these objects floating around for it to be common visitors, I would think.
I don't know.
But we don't know.
That's
good point.
You have to do the experiment.
Yeah.
You have to do those observations to see.
You can hypothesize, but in the end, it's experiment and observation that.
Well, I remember, wasn't that long ago where you didn't hear anything about this kind of stuff.
Right.
Very rarely did anybody ever mention
That's
the possibility.
True. In our lifetime, there's been 3.
Yeah. And it's because we start to look for these things. Hey, maybe there's lots of them out there. Let's start looking and doing these surveys and finding these things.
You could be right.
You never know, right? You have to do, Vera Rubin telescope, because of the LSST, surveying the southern sky, completely once every 3 nights or so. That's going to find.
These are common. It should pick it up.
And it's going to be able to look at the same area, go over again every few nights.
Right. And
the software and that's been developed, the different various pipelines, they're set up to find stuff that's moving, stuff that's changing, like its position, and so they should be able to find. Remember the first light images? They found over 2,000 asteroids that we didn't know existed before.
Right.
So that's the kind of thing that's going to happen. So that's going to be cool to see how this all plays out in the not too distant future. You only have to wait over the next year or so. You'll probably find a lot more from the telescope.
Yeah.
And if you do, think of us.
Think of us. Yeah.
Okay.
So
now the next item, which I thought is kind of cool, is an update, finally, of the search for dark matter. There's something we went on a little bit last day, you remember, about dark matter. So we're going to go in a little bit more depth here today as well. This is a paper that's presenting the results from the Lux-Zeppelin experiment. And just to read the title, it says Dark Matter Search Results from the 4.2 ton years of exposure. Now, when you in the business of detecting dark matter, the 2 things that matter, number 1 is the time of exposure, that is your instrument, your detector, looking for dark matter particles. You could let it run for 500 years.
Mm-hmm.
But who's going to wait that long for your thesis to be finished? Your committee is not going to put up with that.
I've never met a committee that would wait that long.
So then you cut back, obviously, on the time. Should you wait a year? Or if these particles are so elusive, maybe on average I need 2 years of having the detector running before I have a decent chance of detecting one dark matter particle. Or maybe it's 5 years. Or maybe it's 6 months. So you're in this problem, you just don't know, right, how long you should look. So what you can do is just periodically look at the data, of course, so you could have the detector running. And the other thing that matters is the size of the detector.
Right.
So this works by, and we'll show you an example of how it works here in a second, but you're basically looking for a dark matter particle that just happens to pass through the detector. Now, these dark matter particles, as far as we know, we don't know what they are exactly. So all of our observations, all of our theoretical modeling that we've done implies that these dark matter particles do not have an electric charge.
They also apparently do not have a weak charge.
Well, we don't know.
Okay.
Okay.
I heard
These
that they
type
don't.
of type of particle.
You know
that
more about this than I do.
Well, the type of particle this experiment is looking for is WIMPs, which stands for
weakly interacting.
Boom. Weakly interacting.
Oh, okay.
So there is some interaction.
Okay.
You see? Weakly interacting massive particles. So they have gravity. In fact, we would know dark matter existed if it wasn't for gravity.
Right.
Right? I mean, these things the evidence have been accumulating for the existence of dark matter basically since the 1920s, so about 100 years now if you want to push it.
Yeah.
Of course, at the time, people weren't really sure of that. The 1930s, and we're going to say more about it later on at the end of the podcast, Fred Zwicky had wrote a couple papers on dark matter, and so he was ahead of everybody almost by 50 years. And then it was really the late 70s, early 80s, that people like Vera Rubin, whom the telescope in the south is named after, of course, and Kent Ford and others, starting presenting evidence of flat rotation curves.
Right.
Which really got everybody's attention because it's hard to get around that evidence, to explain it without invoking something additional.
And then in the 80s and 90s, we got Hubble starting to show things like the bullet cluster and other clusters.
Yeah, gravitational lensing effect, all kinds of stuff. In fact, with very good measurements, precise measurements of the leftover heat from the Big Bang, the cosmic microwave background, that tells you what the total composition, matter plus energy of the universe is. In other words, it tells you information about the geometry of the universe. And we know from measurements of things that we can see that there was not enough material in the universe to make up the geometry that was implied by the CMB measurements.
Right.
And so that turned out to be, another way of evidence for dark matter. In fact, we can do very precise measurements today, and that evidence is pretty solid. Right? That there's this additional components. It turned out to be dark matter and dark energy that explains the geometry of the universe and therefore the fluctuations in the temperature of the leftover heat from the Big Bang. That's a whole podcast if you want to go down that rabbit hole, by the way.
I don't know that to hear you talk about it when we get on this topic, it's 2 or 3 podcasts.
I just thought of that maybe we should have a guest on who's an expert in CMB to explain in detail how do you know from just the measurements of the fluctuations of the temperature of the leftover heat that there's this dark matter and how much it makes up the known universe, and there's evidence for dark energy and all this kind of stuff. It'll be kind of fascinating to go down that.
Do we know? Well, we'll talk about that after.
We can come up with some names. I don't think that's not too difficult.
Okay.
But anyway, so we know dark matter exists because we detect its gravitational influence on things that we can see directly. Mm-hmm. And that would be, for example, why objects in the outer part of spiral galaxies like our own Milky Way are traveling too fast in their orbits. Right. And the only way they could be unbound, we're talking about bound and unbound orbits today, the only reason they could have bound orbits is there must be a lot more gravity that makes up our galaxy that's holding on to those fastly moving objects.
And if there's more gravity,
there has to be
more mass.
More mass. And if you look around at all the different wavelengths, all the way from radio to gamma rays in the electromagnetic spectrum,
the mass just isn't
It's just not enough mass. You need a lot more mass. Roughly about 85% or so of the Milky Way's mass is in the form of this dark matter.
Stuff we can't see in any of these wavelengths.
Now, if it doesn't give off light, then it's not electrically charged.
Right.
And so you run into the problem now that this stuff becomes extremely elusive, hard to detect directly. One way of detecting it is if these dark matter, if they're made up of, let's say, subatomic particles, and we don't know that's the case.
Right.
So we always have to make sure that we say that caveat.
Hence the dark is part of that is we don't know.
Mystery. So if one of these dark matter particles hits something that we know exists, such as, let's say, an atom of known material, let's say a xenon atom.
Okay.
Then the energy that gets imparted to that xenon atom is such it can strip away one or more electrons.
And that's going to emit light.
And those electrons, if they're traveling through a bath of fluid, can travel actually faster than the speed of light in the fluid, not faster than the speed of light in a vacuum of space. And when you do that, you release Cherenkov radiation, which is blue light. And that's exactly what you see what's going on here in this illustration, the drawing that's on the left side.
If I'm remembering correctly, it's a very specific wavelength of blue light, too, isn't it?
Yeah, and so it's easily detected by photomultiplier tubes.
Okay.
And so as you can see there, you have a vessel containing fluid, and you have photomultiplier tubes, and in this illustration, there's a set of them above and below. And as that light spreads sort of in front of the electron as it's traveling, it'll intercept several of these photomultiplier tubes, and you get this sort of ring of blue light that's detected from those fastly moving electrons. And so you can work backwards. What is the energy that was required to generate the light that you see? And then how would that be produced, in terms of the collision process? What particle could do that? What would be the energy, or i.e. the mass of the particle, the incoming particle? and see if it has the properties and characteristics of a dark matter particle. Now,
because it could be a neutrino as well, right?
yeah, and those we would know
the same
because we
method
know
that we detect neutrinos.
Yes,
with.
exactly. So you can isolate it by knowing the characteristics of the properties of the scattering event and the detection that occurs. Now, and of course, you want that to repeat.
Right.
There's been
kind of useless if it doesn't.
Well, I think since the 80s or 90s, right? I mean, other experiments in different countries around the world have reported detection of a dark matter particle, but it was a one-time, one-off thing.
Right.
Nobody else who was running an experiment then or later that would be sensitive to the same type of particle properties that they claimed the detection, never seen anything.
Right.
So it's like you have to confirm it. In science, we always want confirmation.
Yep.
Always confirmation. And so far, there's been no confirmation of any dark matter particle detection.
Okay.
Now, if you go back one slide, this is the paper that was published. So this is in July 1st, if I'm not mistaken. Yep, published on July 1st. They're reporting the present day results of one of these really good experiments that's running now, the Lux Zeppelin experiment. And they report the fact that they've never seen anything, no detection. So it's a null result again.
And 4.2 ton years. So this you can get that by either having your detector filled with 4.2 tons of the material, which...
Right. So you multiply that factor, right? So this experiment, if you read the abstract, it has 3.3 ton years, 280 days that they've been running on one case, and 4.2 ton years, and where they were running at 220 days.
Right.
So they're over 200 days running this experiment with, on the order of 4 tons of liquid.
Containing xenon.
Well, multiplied by the factor, the units,
Yeah.
ton times the time, right? Yeah, containing the xenon.
And that's what I was getting at.
Yeah.
You can get a ton year by having 1 ton running for one,
One
year.
year.
Or, 2
multiple
tons
tons
running
for a fraction
for
of a
6
year.
months or something
Yes.
like that.
Exactly. And so you want that number to be as large as possible.
Right.
That's the thing. You want the time to be long and the amount of liquid, so the tonnage, to be high as well. So you want that product then to be as large as number as possible, because that'll just increase your odds of detecting dark matter. So unfortunately, there's been no detection. Now, the next slide on the right in this time kind of gives you the parameter space, the different properties of the dark matter particles that are sensitive by this type of experiment. And that's one of the problems here. This experiment cannot detect any possible dark matter particle that you can hypothetically propose to exist. It's only sensitive to a certain range of properties. And that's the only sort of niche that you can look at.
And that's true of all of these detectors, though.
Every detector, right? There's only a certain range of properties that you're sensitive to, which means that if you don't detect anything,
it just means it's outside your parameter.
It's outside your ability to detect. The properties are such that you can't see it. So you have to do something to your experiment, make it run longer. Mm-hmm. So increase the ton year value, or have some other way. Right, maybe increase the amount of liquid that you're using, your xenon detector fluid, right? All of these kind of things, or maybe a totally different experiment altogether, in order to, if you like, probe parameter space that it's outside your ability to detect with your present experiment. And that is why
there's many of different variations on this type of experiment that are running right now, is because they're all looking at different parameter spaces.
Yeah, and that's why you're saying, okay, dark matter doesn't exist. Well, what do you mean dark matter doesn't exist? Well, the detector's been running since the 1980s. They haven't seen anything. How many years has that been? 40 years? Come on now, right? There can't be any dark matter. But wait a minute. All we can say is that for dark matter that has a certain range of properties, they don't exist in nature, or we would have detected them.
Right.
But there's a whole slew of particles that you can look at or theorize that have properties that right now any of the detectors are not sensitive to.
And there was what we're aiming at. Yes.
You see? So it's a never ending. And by the way, if dark matter doesn't exist, then you got to explain all of the effects that we could see due to gravity, like the bullet cluster that we talked about last week, and other things, the flat rotation curves, the gravitational lens effect, the CMB measurements. It goes on, goes on, and goes on. And then that's why there was this group, I think they started like in the 1990s, looking at modifying Newtonian dynamics, change the law of gravity such that it makes it that dark matter is not needed, that it can be naturally explained by the law of gravity that's altered.
And one of the fatal bullets for that theory or that hypothesis has come about also. Haven't they started seeing the drop-off, the decline of the speed curve on the Milky Way?
Yeah, in the Andromeda Galaxy.
And if Mond was correct, there would be no drop-off on that speed curve.
And the biggest one was always the bullet cluster. And now we have even more precise mass measurements made from the James Webb Space Telescope from recent observations. And you need dark matter to explain why, for example, you get this colliding of hot gas in the central region and this sort of shock wave that you see that developed, and yet you see the two clusters themselves sort of pass through each other and gone out the other side now, and you can measure their mass through gravitational lensing effect, and they have a lot of mass. They have dark matter.
Right.
And so you need dark matter to explain those observations. And so, with MOD, you might be able to get away with saying you need less dark matter than without MOD, but that's not the point. If you need dark matter, you need dark matter.
You still got to explain what it is.
Yeah.
And we're still poking around trying to figure that out.
Now, if there's some other way of modifying gravity, other than the present sort of ideas that people had for MOD, then maybe that would work, but it'd have to be modified in a very specialized way. And the other thing is you can't just go, it reminds me almost, Robert, you think way back in the time of Ptolemy, back when you were a little baby.
Right.
When they were trying to come up with a model of the solar system.
Mm-hmm.
And remember the epicycles with an epicycle, all this machinery to try to explain the change in brightness of the planets and the retrograde motion. There was no reason to do that except empirically trying to match the observations.
Right.
There was no fundamental, if you like, reason why, from the point of view of physics, why you would have that type. It was so contrived, the model.
Right.
So that's the other thing. You need to motivate the theoretical underpinnings of the explanation for dark matter. You can't just assume all this, the way gravity is all. Why is it like that?
Right.
And we have a good understanding of gravity today. That's the general theory of relativity.
And I was going to mention that general relativity works. It is one of the most tested and most verified theories we've ever come up with. So you're going to have to explain not only how your theory works and why it works, but why it leads to GR and it working too. And I'm going to sit here and tip my hat, lean back, snicker, and say good luck.
Well, it's a classic everyday use of general theory of relativity. And if the general theory of relativity never worked, you would notice it.
Right.
What is it?
That's GPS.
The GPS system.
Yeah.
The global positioning system. It works because of special relativity and the general theory of relativity.
And they tried it without making those corrections. And the positioning drifted over time. Only when they corrected using GR did suddenly everything stay stable.
Yeah, it needs SR and GR.
Yes.
And the reason for it is because the satellites are in motion and orbit around the Earth, and they communicate with ground stations that are stationary. And then on board the satellites, there are atomic clocks. Those clocks are moving.
Right.
And those satellites are moving relative to the ground station. So then you have time dilation, that's special relativity. And those clocks on board those GPS satellites are further away from the center of the Earth than the ground station. So time runs slower on the surface of the Earth than it does further away in orbit where the satellites are. That's the general theory of relativity.
Right.
So you need both corrections, and they don't cancel each other out. Some people I've seen somewhere where people were suggesting that. No, the effects are different. And the numbers that you get are different. They do not cancel each other out. But with those corrections, then we have the GPS that we know and love today.
Right. And it's down to what? Centimeter precision?
Yeah, I mean, it's very precise.
Holy cow.
So it works. So if the general theory of relativity, our understanding of gravity, modern understanding, didn't work, then we wouldn't have the GPS system. So you always use that as an example. We know that we understand gravity, at least to some level.
Right.
Do we have the ultimate word on gravity? Probably not. Because we can go down this rabbit hole of talking about quantum mechanics.
Right.
And how GR works at the quantum level, and what does that mean? And the way you think about it is what happens at the very center of a black hole.
And right now, GR says you're dividing by zero. You've got a singularity, which means we can say nothing.
Yeah. So we have some issues that need to be worked out. But at least operating in a regime where it's applicable, it works just fine.
There are still chinks in GR, but they're chinks. They're not gaping holes or anything.
Yeah.
So.
Okay, so the story of dark matter, then we'll have to wait. So hopefully, a not too distant future, at least hopefully in our lifetime,
maybe we'll see something.
We'll see what the dark matter actually is, or get a good advance made in that subject. Now, the other news item, the final one I want to share with you today, Robert, and everyone else who's watching, is that we've had, for the first time, which I thought was quite unusual, a flash potentially on the surface of Saturn. And you can see that on the left side of this image.
Right.
So this image that was taken by Mario Rana, R-A-N-A. So he was monitoring Saturn, and he, in his image that he took, is taking a video of it, that he saw this flash that you see there with the blue cross that's at the center. But the thing is that real or not?
That's a pretty poor
image. It looks like it was taken almost like with one of
rings are, but
it looks like it was taken like almost with the night scopes that you can buy now for telescopes, right?
Yeah.
So I don't know if that's the case or not. So this was taken not that long ago, on July the 5th, between 9 and 9:15 UT time. And if anyone else happened to be taking an image of Saturn at that time and seen anything, then of course you should say something.
You should say something, please.
Because we're trying to confirm whether or not this was an impact, and most likely it would be maybe of an asteroid that hit the surface of Saturn. But yeah, not seeing any impacts at all, it's kind of weird. We've seen impacts on the moon.
We've seen them on Jupiter.
We've seen them on Jupiter, Shoemaker-Levy 9 being the obvious one, when the comet and all its pieces that broke up hit Jupiter, multiple times over a few hours.
That was a neat.
That was cool. Yeah,
got to do seismology on Jupiter,
and it left marks on Jupiter. You had spots, dark spots, where it had interacted with the material. So yeah, there was a lot. Look up Shoemaker-Levy 9, and
you'll see why. Some of us are still giddy over that one.
That was like in 1992 or something?
Something like that.
It was on that order.
Undergrad, so yeah.
I remember they took Hubble Space Telescope images of it as it was happening almost near real time.
Right.
So Hubble was launched, I think, in 1990, or if I'm not mistaken, around that. Yeah. So by the time they had it repaired, so it wasn't like blurry images. They had managed to get it repaired by then. So yeah, that was cool. And luckily, none of those fragments intercepted the Earth. We wouldn't be here doing this podcast.
Yep.
It'd be game over because they were fairly large.
They were large.
Yeah, and the effects, I think, on Jupiter lasted for months.
Yeah.
So it took a while.
That's what I'm saying. We got to do seismology on Jupiter because we could see the ripples in the atmosphere, the wave patterns, for a week or more afterwards. So they were large enough that they put up that kind of ripple in Jupiter's atmosphere that we could see it from Earth for several days at least.
Right, and Saturn is less massive than Jupiter, but Jupiter, we know, acts as a sort of a vacuum cleaner in some sense. It takes a lot of the impacts in our solar system, so it's a nice bullseye target. Right. So a lot of things that are flying around, like asteroids and comets, then intercept Jupiter and have done so in the past. So you're clearing out a lot of the objects that ultimately may pose the risk in the future to our own planet.
At the same time, though, it could be kicking some at us even faster than they would have normally been.
It's my understanding. It's mostly a clearing out effect.
Yes.
So it helps. In fact, the book Rare Earth, Peter Ward and Brownlee that wrote the book, one of the things that they argued in terms of, is there intelligent life elsewhere in another planet orbiting another sun? And the idea, well, the chance is pretty rare. Why? Because you need all these things to go right, like having a Jupiter-like object in the solar system that can take the hits.
Right.
To prevent mass extinction occurring over many, many, many times, after just a million years, and everything goes extinct or nearly extinct again. And you don't want that to happen, right? You need a long period of relative stability for eventually intelligent life to form.
For an Earth-type life
Yeah.
system, yes.
Right. We're not talking about bacteria or viruses or that kind of order, but something that would evolve to the point where you could build telescopes.
Right.
You know, that sort of thing, right? So that's the idea. So that you need that kind of thing. And Saturn, in a way, provides the secondary backup to Jupiter. So you know it's going to have to get walloped, right? It's being hit.
So yeah.
So that's why I find it weird why
that we haven't seen it.
That's it. That's the thing.
We've been looking through telescopes at these objects
since 1600s, right?
Yeah. So what, 400 years now?
And then how long has it been since we had any really good, decent telescope? Since probably the 1800s that you would see a lot of these features. So, yeah.
So,
anyways, yeah. So it's kind of interesting why we haven't seen anything for now.
Yeah.
But. You know, all of this work, of course, whether or not we're talking about objects that are inbound from outside the solar system, whether we're talking about instruments or experiments that we need to design, maybe new ideas, new way of thinking to find the dark matter particle, to finally solve that. And by the way, if you discover what is the dark matter, you know what's in your future.
Trip to Sweet Stockholm?
Yeah, you pick up your Nobel Prize and the money that goes with it.
Absolutely.
Moolah.
Yeah.
But you have to do a lot of work to earn that, though.
You have to do a lot of work to earn that.
Unfortunately. But the starting point in all of that, if you want to think of that as maybe in your distant future, is higher education.
Come see us here at the University of North Dakota or any place, but we're particularly partial to University of North Dakota. They have many programs that are online, so you don't even have to show up here. But if you do come to campus, by all means, look us up. Wayne and I, we're here. We're happy to talk with you. But the bottom line is you should continue your education. You should keep learning new things, and working with us here at the UND is a perfect way of doing that.
Now, our next podcast is next Tuesday, July the 15th. Oh, my God, the summer is going too fast.
Isn't it, though? I've got so much to do, and I haven't been able to get to it.
There's two things I look at for seeing how fast time is elapsing.
Okay.
The one is seeing what the date of the next podcast is. That's a scary one. The other one before that is look at what is the expiry date on my milk.
And here I was thinking about when your tag expires on your car, you know.
Well, when your milk expires and it's December 25th, you know, Christmas is around the corner, right? It's not too far off. It's time to start shopping. You know?
Time to start shopping.
Well, you got to be in the mood, right?
Hopefully you've done that before.
Well, you got to be in the mood, Robert.
Okay,
You don't believe in Christmas in July, do you? Now, so
Christmas
our next
shopping in July.
Some people have Christmas in July.
That's true.
Hallmark movies. That's when they filmed them, right?
Yeah.
With the fake snow.
Ching, ching, ching.
Yeah. Yes. So our next podcast will be 1 week from today at 5 o'clock Central Daylight Time, as always. Now, we always leave you with a quote at the end of our podcast.
Okay.
Today's quote is related to dark matter. So I knew we were going to talk a little bit about dark matter today.
Okay, so I'm guessing Zwicky.
Fred Zwicky, who is arguably the one that came up with the greatest source of observations to support the presence of dark matter.
Okay.
I mean, there was others before him, but
he coined the term, didn't he?
Yeah, he did. He used the term dark matter, so we'll go with him. This is in 1933, so nearly 100 years ago. It's getting close.
Getting close.
And it was a paper that he published in to us, an obscure journal. It was published in German, so we have to look at the German translation. And here's what he said. If this overdensity, that's what he was talking about in matter, is confirmed, we would arrive at the astonishing conclusion that dark matter is present with a much greater density than luminous matter.
And that's what we're finding.
And it really sort of hits home when you think that people really didn't pay attention to that statement or anything else for almost nearly 50 years before astronomers finally realized, you know, there's something to this. It's actually a major part of our universe, and we better find out what it is.
Well, you know, the guy who first hypothesized the solar wind was laughed at for, 10, 15 years before they finally
Eugene Parker. Yeah.
Before they finally picked it up.
Well, didn't they laugh at the people who said that the continental plates move apart?
They did. They did.
Tectonic activity, right?
And
Tectonic
then they
plates.
had all these other lines.
Continental
of evidence. Continental drift.
Yeah.
Had all these other lines pointing to the same thing, that there are plates and they move.
And the thing, too, because you can look at the map of the Earth and always could fit together like a jigsaw puzzle,
That was
right?
one of them, yes.
Yeah, for sure.
That was,
Anyways, if you like this podcast, please don't hesitate to give us a thumbs up. Subscribe if you haven't subscribed. Tell your friends about us.
absolutely.
Maybe there's people out there interested in watching our podcast, things that we've done in the past and will do in the future.
Yep.
And thank you very much for watching.
Thank you, folks. Have a good day.